way is this guy going? Left or right at time 0? I heard somebody say it. I'm right here with center of mass. I'm watching the system. I'm moving that way. He's coming toward me from my perspective. And you say, well, that's not right. You're the guy's moving out. Well, motion is all relative. Even Einstein agrees with that, right? So they call it relativity, to be honest. So, but there was the Galilean relativity we're talking about right now. We can just add and subtract things and it all works out. So this guy's going that way from my perspective. And so I can say, all right, this is VB 0, it's prime. What does it equal? It equals negative 1/2 VA 0 with no prime. This equals 1/2 VA 0 with no half. I hope I guess you can see it up there. I hope you can. What I've done is I've just subtracted the velocity of the center of mass from each of these velocities to get the relative velocity of those two objects. Relative to what? Relative to the center of mass. I said, how do I calculate in general some velocity? How do I calculate this? The prime velocity. You say, well, it's the one I started with, minus the velocity of the center of mass as measured in the original reference frame. This is just the equation in the book you've seen for relative velocity. And so just to make sure that makes sense, we already figured out what the velocity of the center of mass was in this reference frame. What was it? Yeah, I heard somebody mumble it. 1/2 this velocity, VA 0. So you can just say, oh yeah, in this reference frame, the velocity of the center of mass is equal to 1/2 times the original velocity. If I switch my A and 0, there's no meaning to the order of my symbols. I'll try to keep them lined up so you can keep it straight. Velocity of the center of mass is equal to 1/2 times the velocity of A at time 0. And so if I just plug it in, right, say, oh, well, that's just VA 0 minus, minus what? Minus positive 1/2 VA 0. So 1 minus a half is a half. So you're left with positive a half. That's where I got the positive 1/2 VA 0. Although we also figured it out just by looking at the problem. Because the problem's simple enough, we can figure out what the answer is going to be before we plug in the equation. And in general, that's the way to go. Figure out as much as you can before you plug your numbers in. Like, get an idea what you expect. Positives, negatives. You can be surprised sometimes. And the problem is giving enough information. But the way I try to keep my head straight, and you see me struggling constantly to keep my head straight, the only way to do it is to have a feeling for what's going to happen. But you have to trust your equations when things are surprising too. All right, so this guy's coming in like that. And look, what I did already, I drew the trajectory of the center of mass as viewed in the center of mass coordinate system. In the center of mass coordinate system, what's the velocity of the center of mass? So if I find the only origin, x equals 0 to the center of mass, how fast is the center of mass moving with respect to that coordinate system? 0. Another way to say that is that v prime sub cm, right? The velocity of my center of mass as measured in this coordinate system, that's equal to 0. That's just a definition, really. That's essentially. So that means that if I draw the center of mass at different times, it's always in the same place. So in comes this guy, he collides, and then what happens? Well, at time 2, A and B recoil and bounce out. This is an elastic collision. They both end up moving at the end, and they wind up moving at the same speed as they came in at, right? But the velocity changed direction. So in general, when you've got a problem with two colliding objects, and it's an elastic, so this whole problem is elastic. It's an elastic collision, and it's viewed from the center of mass. It turns out, and this is why it's simple to think about, that you can, if you know the initial velocities of all the objects, well, both objects, two objects in the problem, the final velocities are just the same as the initial velocities, just with opposite signs, right? Remember in this problem, or I should say it's the same problem, just viewed in this reference frame, what happened was one guy was moving in the beginning, the other guy was moving at all. Then there was a collision, and then at the end, the first guy's not moving, the second guy's moving at the same speed as the first guy was, right? They sort of changed who was doing the moving. But if I just change the perspective of the problem, if I view it from the center of mass, because they have the same mass, they're both moving at the same speed, opposite directions, they bounce off each other, and then they move at the same speed outward, and so you just change the signs of all the parts. Now suppose the masses were different. In that case, it would still be the case that you just switch the signs before and after for each part individually. So if suppose A were more massive than B, right? What does that look like on here, by the way? Let's see what that looks like. All right, so here I've got it's a Mack truck and it's a terrible name. Mack truck and then Honda Civic, So no, that's terrible. Bicyclists, no. Let's say bumper cars, and there's two kids in this car and one kid in this car, right? So it's more massive. Nobody's getting hurt. All right, so it's a big object that's going to be moving. So what happens? If the big object does the moving initially. So in the lab frame, these guys are holding. Oh, this guy's holding still, and these two guys in a big heavy car. It's coming barreling in. What's going to happen? So is this guy going to bounce off? You're going to bounce. It's going to be an elastic collision, so I know that kinetic energy will be conserved, right? They're not going to stick together, they're going to bounce off each other. But it's going to wind up coming back the way it came from. No? You guys know about the midterm, aren't you? Okay, so let's see. All right, let's find out. This is on the second midterm. All right. I don't know if this is the exact problem, but All right, so here comes the big one. Small guy's holding still. Oh, he keeps going. You see that? But it's complicated with 3. Anyway. All right. Not that complicated. Yeah, so you saw what happened. He kept moving, but he slowed down a little bit, right? Bang. Oh, yeah. Too much fun. All right, so what happened there was this guy came in moving at some speed. He bounces off him, and he flies away, right? And he keeps going, but not as fast. And that solves both conservation of kinetic energy and conservation of momentum. You both must be conserved because it's an elastic collision. I know it's elastic because the problem description told me there were springs on the front, not magnets, or bumpers that could get smashed together or something like that. So what does that look like? What that looks like is, here, so let's say MA is bigger, well, not much bigger, but it's bigger than MB. So in that case, if we watch it from the center of mass coordinate system, let's do that. If we watch it from the center of mass coordinate system, well, where's the center of mass? Closer to the big one or the small one? The big one. So that means that relative to the center of mass, the big one has a smaller speed, right? In other words, I'm going to be like, let's say this is twice as big as him. I don't know if it's exactly true, but that's close to true. So that means it's going to be like 1/3 of the way. Does everyone see that? Okay, go 1, 2, 3. So that's where the center of mass is going to be. If we went through the equation, right? And so that means that as I walk along, I'm moving faster than just half. From the laboratory perspective, I'm moving 2/3 as fast as that guy is, right? And what I see is he's still moving back. He's moving that way relative to me after the collision, but not as fast as he was moving forward. What does that look like? Well, let's do it again. This was the center of mass frame. Same thing here. We'll do, MA bigger than MB, and this is again elastic. And it's the center of mass frame. Okay? What does that look like? Once again, we know center of mass is not moving, right? At every moment in time, it's in the same location in space. The more massive object has to be closer to the center of mass than the other object at any moment in time. By how much? Well, by the ratio of the masses, right? So if this guy's twice, suppose, let's make MA equal to 2 times MB. So we're being really quantitative. It's twice as heavy, twice as massive, I should say. Well, all right, that means that B is right here, and that A will be right here, right? And from the center, and again, the initial situation we had was where, by that I mean in the laboratory, what happened was this guy was moving and he was holding still. We go to the center of mass, though, and they're both moving. Are they both moving to the right, to the left? Well, he's moving to the right. Yeah, they're going right for the middle. And he's going twice as fast as he is. That's how come they meet at the middle, even though they start further apart. Oh, A starts further apart than... Oh, did I draw this backwards? I think I did. I did. I don't know, I was thinking... That makes me feel better. I think A is more massive as I drew it here. Yes, so that's what I meant to do. A on the left, B on the right. A is going to the right at a speed that's half as great as the speed of B. They have equal and opposite momenta, right? They must, because I'm in the center of mass coordinate frame. Then they collide. Here's B, here's A. And then they fly apart. And exactly how fast they fly apart? The same speed that they came in on, just the opposite direction. So I'm not doing this with equations right now. I'm just drawing pictures of what it looks like and thinking through, just using sort of physical reasoning and watching what happens when I walk along on the air track. You don't have the air track on exam, I know, but you wouldn't want to do that anyway. There's a few cases that come up all the time. What comes up? Two objects collide. This is all one-dimensional collisions. You have two objects. In general, they have different masses, and if you think about it in the center mass coordinate system, which you can get to by taking all the initial velocities and subtracting the velocity of the center mass, what you get is exactly the scenario. The objects start at distances that are the ratio of distances is the same as the ratio of their, inverse ratio of their masses. They're coming in toward the center mass. They collide. They bounce away with equal and opposite velocities as they started with. Now, suppose they stuck together. What does that look like for this problem, or even for this problem? Well, and sticking together, I keep asserting over and over again, is maximally inelastic. Here's what I mean by that. When the two guys come together, right? Let's do same mass. All right, here they are. Same mass, come together. This guy's holding still. This guy's moving. Oh, he's trying to escape. Okay. All right, hold still. All right, in he comes. Bang. They keep moving together, but you see how it slowed down? I'll do it again. So he's coming in pretty quick, and then they slow down. Well, I should say he slows down. The second guy sped up. He was initially holding still. The final speed is half the initial speed of the one mass, right? Momentum is conserved because mv, well, these have the same mass, we'll call it m. Initially, we had how much? We had mv, and I'm just saying v for the initial velocity. And at the end, what do we have? Well, the velocity was half as much. It was half v. But there's two masses moving. It's 2m. 2m times a half v. Oh, yeah, the 2 and a half cancel, still mv. Momentum is conserved, as advertised. But what about the kinetic energy? Well, it's just like the problem we solved over here for the bullet. Kinetic energy is lost. In fact, half of it is lost. You started off with 1/2 mv squared. They collide. And after that, you got half the velocity, but twice the mass. So you get a factor of 2 from mass, but you get a factor of 1/4 from velocity squared. Right? Kinetic energy is 1/2 mv squared. And that's the same thing that happened there. When we squared that mv over mw, right? That gave us twice the factor of, in that case, twice the factor of 100. In this case, twice the factor of 2. So you get 2 factors of 2 on the bottom, 1 on the top. When the dust settles, the final kinetic energy is 1/4 mv squared, where v is the initial velocity of this guy, and m is the mass of either one alone. If we do it from the center of mass coordinate system, though, and they stick together, this is inelastic. This is maximally inelastic. Look what happens. You start off with 2 times 1/2 times 1/2 mv squared. So you start off with 1/4 mv squared collision, but then they wouldn't fly apart. They're stuck together, right? So it's maximally inelastic. There's no kinetic energy when it's done, as viewed from the center of mass coordinate system. In other words, if I watch this again from the center of mass, what do I see? This guy's moving that way, he's moving that way, and then they stick together. Nobody's moving for me anymore. They're just holding still. So from the center of mass coordinate system, yeah, a maximally inelastic collision results in no kinetic energy at the end. That's why we call it maximally inelastic. And you might ask, well, wait a minute, are all inelastic collisions maximally inelastic? And the answer is no. Most collisions are somewhere in the middle. You lose a little bit of kinetic energy to heat, to the sound of the collision, to bending the bumper, whatever it is, but there is kinetic energy at the end, even as viewed from the center of mass coordinate system. So we're really studying two extreme cases when we talk about elastic collisions and maximally inelastic collisions. And if you're given a problem, as can happen on an exam or on the homework, that's not necessarily maximally inelastic or elastic. It's in the middle, in fact. Then you have to use your wits and figure out, based on what information you're given, right, what the final outcome, well, depends on what you're asked. You're asked, what's the velocity of, the puck or the whatever it is after the collision? But it's not guaranteed to be elastic, or maybe you're even told it's not elastic, and yet the two objects don't stick together. If they don't stick together at the end, it's not maximally elastic. Because as viewed in the center of mass, there's going to be motion. There will still be kinetic energy left over. And if you still have motion in the center of mass coordinate system, that means that any coordinate system you view this system from, right, it's going to have some kinetic energy. There's going to be some motion. The least motion you can have is the one where you move yourself right along with the center of mass and view it from that coordinate system. Right? So you'll have to use conservation of momentum, and then they'll have to give you, the question must have some extra information in it. Because if all you know is the initial velocities, so in this problem we're trying to figure out what the final velocities are going to be. And so let's count equations and think this through. So if we're doing collisions in one dimension, we've got conservation of energy, one equation, conservation of momentum. Well, in one dimension, momentum is a vector, but in one dimension, momentum is only one equation. You only have two equations from those two conservation laws. But that's okay. You only got two things you're trying to get: final velocity of A and final velocity of B, which in one dimension is just a number for this guy, and a number for that guy. Might be negative, might be positive, but just one number each. So you're trying to get two things with two equations, two unknowns and two equations. I can handle that. Right? That's good. But suppose you're in two dimensions. So just for fun, we'll do a little air hockey, and I'll show you two dimensions. This is I hope this alleviates your concerns a little. Two dimensions is not going to play as big a role in the class. You will not be tested. I won't test you on a two-dimensional, even on the second midterm on final. I won't test you on a billiards problem that's actually a full two-dimensional problem. But you may have homework on it, and it's sort of fun to think about. So real quick, I'll just show, and it also helps you realize what it is that's actually. Is there a question? So, there's a ghostly voice. Do you all hear it? I think there's a ghostly voice. My voice carries too. If I'm in the back pocket, I'm sure the other professors are. Who's talking? All right, here we go. Is this working? Oh, it's working. Can you see it up on the big board? Oh, there you go. I'm a master hockey player, so I'm going to do. Actually, this is more like billiards in a way. Oh man, this thing's really. Okay. That's funny. Let's see. All right, I'll do this. So here's what I'm trying to do. I'm trying to get this guy level enough that he won't float away on me. Now when I collide, oh, it's too hard. I need to shim him up. They do have little shims on them. Let me do this for a second and see if I can get some satisfaction. I don't know if it's going to work. Just one more try here. All right, how's that? That's a little better. Let's try that. That's a little better. So what I'm going to do is I'm going to come in here and collide with this guy. I'm going to aim right at him and see what happens. If I go right out and they hit dead on like that, then it's really just a one-dimensional problem. And we know how to solve that with those equations. Here it goes. Bang. Oop, you kept moving. It should be the same mass. Should have stopped. Try it again. That sort of worked. Sort of worked. You can't see, am I doing this? All right. I know. All right. Here's my thing unobtrusively from the corner. Ignore that hand. Oh, my head's in the way. My nose is in the way. All right. Let's try this. Is that better? Oh, yeah. You guys were missing out. Oh, it kept moving, but it shouldn't have. Well, that was a better one right there. In came one guy, the other guy stopped. All right. But you know what happens if you aim off center, right? If you aim off center, then they fly out, not in a straight line, but they fly out like this, right? So if you're a pool player, right, if you spend your evenings at the pool hall as I do, what happens is, in comes the puck, not puck, the billiard ball, right? And depending on exactly what the alignment is, you get a different outcome. In other words, if it hits right here, they'll fly off like that. If it hits dead on, I got too many pucks. If it goes like this, it goes like this, right? It goes over here, excuse me, over here, it goes up like that. And if it goes dead center, then this guy keeps moving and he would hold still. The thing is, if you're a really good pool player, you know how to do all kinds of things like spin the ball, and friction plays a role in pool. Even the billiard balls that are really hard and smooth, they're almost friction-free in a lot of circumstances. If you're spinning the ball hard enough, especially if you got chalk on there, use a chalk to add friction, right? To add static friction, to increase the coefficient of static friction at the end of your pool cue. If that dust is on the ball, that has an effect. The felt itself on the table, it provides pretty high friction, right? And so there's all kinds of friction involved. But if you forget the friction for a second and just ask about collisions and say, what if I just have an elastic collision between two round objects, right? Well, how many equations? If you're in two dimensions, how many equations do we have? We've got conservation of energy. Well, even in two dimensions, energy is just a number, just a scalar. So only get one equation from conservation of energy. 1 half mv squared, sum of 1 half mv squared initial equals sum of 1 half mv squared final. And then you get two equations from conservation of momentum, right? One for the x direction and one for the y direction. So you have two equations from that, but that's only three equations. And if what you're told is here are the initial velocities of the two pucks, right, or the two billiard balls, where they are. One's holding still, so velocity 0. The other one's moving in some particular direction. Well, that's four numbers you've specified, right? But now you're trying to get four numbers out at the end. You want to know what the velocities of the two balls are, and each of those balls have two-dimensional velocity vectors. That requires two numbers to specify. So you want four numbers out, but you've only got three equations going in. So you need one more equation. You need some more information. And that information is embodied in this discussion we're having about whether or not this guy was lined up and hitting him dead on, or whether he's a little bit off. And notice that there's only one degree of freedom left. There's only one unspecified number's worth of stuff at the end, right? That's why it is that when you play pool, you can't separately control the angle this guy would go and the angle this guy would go. If this guy goes at a steeper angle, he's going to go at a steeper, meaning further from that line. If this guy goes at an angle that's more has more horizontal component compared to that, then this guy will too, right? And you know that from conservation of momentum. If the momentum initially, this guy's moving that way, his momentum initially is 0 in that direction. So the system has 0 momentum pointing in that direction, right? And that means that after the collision, they have to, if this guy has any component going that way, he has to have a component going the opposite direction. So you only have one degree of freedom left over, and then billiard players get around that by spinning the ball. And so then what happens is, the ball taking a curving trajectory, all kinds of things can happen. You can have them, because there's friction with the ground, and there's other things happen too. But if you forget that, think about it in terms of an air hockey table where there's no friction with the ground, and essentially no friction between the pucks, just normal force, just banging against each other, normal force. Then what determines what angle they go out is exactly what the angle of the interface is between them, because it's a normal force between them, a force that's pointing perpendicular to that, pointing to that surface. Anyway, he makes that in homework. But I think it's worth thinking about two dimensions though briefly, just to get reminded, like the reason we're able to specify the outcomes here for an elastic collision, we have enough equations. We've got two equations, two unknowns. And it happens in this class. I mean, you may see problems on the exam, right? Even this week's exam, where it may even secretly be the case that there are more equations you might think you need, depending on how many unknowns crop up when you try to write down the equation. So you got to keep track. How many unknowns do I have? How many equations do I need to solve that? And if you don't have enough equations, come up with another equation, right? You don't have no matter how many you manipulate just two equations, you need three. You have three unknowns. You need another equation. So just make sure, and you have to be linearly independent. Right? So make sure that you got three separate equations. Anyway, all right. So let's talk through one more thing about back to one-dimensional collisions. If you have a wall in the problem. So just like if you're playing, suppose you're playing, as I used to do when I was younger, until I would lose all my tennis balls in like 20 minutes. I with a racket, I sit over the tennis ball and bounce it against the wall, right? And it would always come back. That's a very good opponent, right? So the way that worked, well, first of all, was kinetic energy conserved with that collision with the wall? For a really good, suppose I got a really good bouncy, a brand new tennis ball. So let's assume, yeah, it essentially would provide an elastic collision against another tennis ball, for example. If I bounce it against the wall, is kinetic energy conserved? It is. In fact, the ball comes out with the same speed as it went in with, so kinetic energy is conserved. And is momentum conserved? So let's think about that. Did we talk about this last time? No, it didn't. So in comes the ball. So here's the situation, right? You got your wall. So here's your wall right here. Wall. Here's your ball. So here's time 0. Ball's coming in at some velocity v, right? And then we'll just skip to time 1. We'll forget about the collision. Time 1, out comes the ball. Same velocity. Now I'm going to say minus v. So here's my x-axis or whatever. And oh yeah, maybe I'll do this. That's okay. I can do that. The problem I don't like to have a v without a subscript or a vector on it with a minus sign in front of a vector arrow because it makes it's like a negative length or something. So what I mean is that the velocity itself changed sign. So v sub x here is minus whatever v sub x would be here. And I'm calling in v as some positive, it's this vector right here. So it's minus that. Okay, flip it around. Great. Super. So kinetic energy was, this is an elastic collision. Kinetic energy is conserved. Yeah, elastic. Right? Now, and we already decided kinetic energy is conserved. But what about the momentum? So momentum is always conserved in every collision. But you have to consider a closed system. So what does this system consist